Alright, hello everyone. Welcome to the 7th tutorial. Today we're going to be talking about clustering. So in class you learned k-means clustering and the way to do that. And today I'm going to show you how to implement it, and it's actually very, very easy. It's a lot easier than doing it manually. So just to reiterate, k-means, the first thing you need to do is determine a distance metric that you want to use. And then what k-means does is it randomly assigns center points to the number of clusters that you want to set. So you set the number of clusters, which is k, and then what it does is it calculates the distances from all of the points, finds the closest points, and reassigns the clusters based off of the average point or the average distance. So it minimizes the distance, and it keeps iterating until the elements in the clusters remain the same. And implementing it in scikit-learn is actually as simple as one line of code. It's literally k-means. You set the number of clusters, and then you just set a random state. So again, the way that it sets the initial points is random, and the reason that I'm using a random state here is so that it's reproducible. So if you were to rerun this code, the clusters would look the exact same. And this is important when you deal with larger data sets. So here we're going to be just talking about 2 dimensions. So here we have x and y data, and then we cluster based off of the distances in x and y. But you can apply this to any number of features. So you can have like 10, 20 features, and it will still be able to do that. And if you read the documentation, it explains how you can set other parameters for k-means. The general default way to the distance metric that's being used is the Euclidean distance, which is just basically the straight line distance between the points. In class, you also learned other types of distance metrics, such as the Manhattan distance or the cosine similarity or various other types of matrices. And those are useful in certain cases if the Euclidean distance doesn't work well or it doesn't really make sense. So for example, if you're using like the cosine similarity, sometimes it works a lot better for document clustering because it has a lot of because having a word in a document sometimes means that the document is about a topic, but not having a word in it doesn't mean that the document is not about that topic. So each distance measure has its own advantages and disadvantages, and there is no real hard science to how to do clustering. What you end up doing is you just try, you can try first different distance metrics or different distance measures, and then what you can also do is try different types of algorithms, which I'm going to show very shortly. So let's talk about some of the assumptions that k-means has. So as you can see here, you can simply just cluster, and then you can just plot based off what the predicted. So here I just make some x and y data, and then we cluster. And in this case, I create the number of samples, and it creates 3 clusters. So now what happens if we have an incorrect number of blobs? So let's say we try and cluster 2 groups instead of 3. So here basically I just run this code, and instead I try and use the wrong number of k. So what that creates is that'll create 2 separate blocks. So these 2 will be grouped as one, and this will be grouped as the other. So if you use the wrong number of k, sometimes you won't be able to cluster as well as you could. And the way to avoid this is you can try and measure. The way to avoid all of this is trying to get an average distance measurement from the center. But again, that's really hard. What you end up having to do is just to plot the data, just like I did, so you can kind of understand what's going on. The other thing that I wanted to talk about is a different distribution. So I applied a transform which makes the same blobs into vertical lines here. And because we're using the Euclidean distance from each point, it's going to set up centers that are around the center, not around each of the lines, but just basically where the groupings of the centers are. So sometimes if your data is not if your data is not in the way that k-means is able to measure the distances, you will get an incorrect result, or the groupings that you get might not be actual natural groupings. So this is just an example of asymptotical distributed blobs. And then k-means is also pretty robust. So even if you have unequal variance. So sometimes if your blobs are further, or your data, the natural groupings, there's a lot of variance in one and little in the other. K-means can still work, again, if the shape is in the shape of a blob, if you use the Euclidean distance. And the same thing is if you have unevenly sized blobs, K-mean will still work. And the reason for that is that it minimizes the distance between each point. It doesn't matter how many points there are. So these are just some examples of some assumptions that will help you when you're actually applying clustering to try and do better if you can. So sometimes clustering is not straightforward, so I recommend trying different distance distance metrics as well as different algorithms. So I don't want to really go over every line of the code in this example. This is one of the examples from the clustering documentation, which I can show here. And if you read through this, it'll explain each of the various different methods. So of course, there's not enough time to learn each and every method in class. K-means is the simplest, and it's the one that you should start with. But if you're finding that you're not getting very good clusters, you can try each of the different types of algorithms to cluster, and you can read the documentation, and it kind of explains what each of them does and how they work. But this is a great visualization that I found in the documentation that kind of shows each of the different types of algorithms. So for example, if you have circular data, K-means will just try and reduce the distance and split the groups in half. If you have data that's in a cone, the same thing. Blobs incorrectly will assign the centers, and it will split. And then there are a couple of each. Actually, I think it's easier to read on the documentation. So if I actually just pull up the documentation, so each of the different algorithms will provide a different output. So if you're dealing with, if you want to be able to, basically, if your data set looks like these cones, you might want to try some of the other types of algorithms. So what I would recommend is, in the beginning, use K-means clustering, and then try and visualize what your groupings of your data look like, and then try and apply the right algorithm. So each one has its advantages and disadvantages. But just looking at this visually, you know that if you have circular data, you can try agglomerative clustering or spectral clustering, for example. And what I would do in this case is, if you know you want to use one of these, you can just basically just search the documentation for it, and if you read through it, it'll explain what the different parameters are and how to use it. And sometimes at the bottom they have examples. So that's what I would recommend. And the reason that I'm presenting this is just because I think you might have difficulties finding those natural clusterings, which is the problem that I had when I work on projects as well. Especially if you're dealing with text data, there's a lot of noise in the data. So it's difficult to be able to cluster, because even if you remove something called stop words, or the common English words like the or like as or those kind of stop words, you will still get a lot of noise, and your clusters might not make sense. Or there'll be some keywords, but it'll be difficult to determine what are the keywords. So another thing you can do is you can use dimensionality reduction to make it simpler, and I'll explain what that is very shortly. So in this example, I just wanted to show an easy example of where we could use K-means clustering to cluster text, not classify, to cluster text. So in this case, there are basically some words, just some strings that I put in here. Some of the text is on human HCI, so basically interface, and the other one is on graph theory. And so I know naturally that there are two clusters, and that's because I set it. In the real world, you won't know what the actual true number of clusters are. You're going to have to try different numbers for K and see the groupings. And then again, what I do here is I vectorize, so I turn each word into its own element and count the number of appearances of that word. But I remove any of the English stop words. So it'll remove in or of or a or those kind of words. And then basically I just use K-means. And here I use 2, but you can use 3, you can use 4. And in a real world, you'd have a lot more than just a small number of documents. And then basically, by running this, you can actually get what each of the top clusters are. So it broke it into 2 clusters, so cluster 0 and cluster 1. And as you can see here, it naturally found like words like interface, human, response, computer, management engineering, testing. And that's more related to HCI compared to the things at the bottom, which are graph, trees, minors, surveys, intersections, which is more related to graph theory. So again, in this example, it just used the text from this and found similarities and naturally grouped these texts into 2 groups. So for example, if you had a bunch of papers and you wanted to determine what are the corpuses about, or what are the papers about, you could just cluster them and realize, oh, maybe there's some that are about human interface, and then there are others that are about math and graph theory. So that's a simple example. I have a more involved example on how to do this. So in conjunction with clustering, there's also decomposition. So so basically in linear algebra, you learned about principal component analysis, where you can find the principal vectors and then reduce your data set down to those vectors and do analysis on that. A side topic that's actually very powerful in pattern recognition and data mining is a thing called latent semantic analysis. And if you Google search it, it will kind of explain to you what latent variables are, but those are hidden variables that are inside of data sets, and you can't measure them directly, but you can infer them. You can also use a concept called singular value decomposition, which principal component analysis is, but there are other techniques to do it. And then you can reduce the amount of components that you have and then cluster on the reduced amount. So sometimes if your clustering is not working very well and you have a large set of data, you can reduce it down. And that is really powerful with text documents. So in my example that I showed last week, when I was doing document clustering, just using k-means clustering gave me a bunch of clusters that didn't make a lot of sense. After I applied latent semantic analysis and topic modeling, I was actually able to determine clusters that were better grouped together. And I found a hidden group in our data, which was French words. So I found papers that were about French. And just using k-means, I didn't even find that at all. So sometimes using principal component analysis is useful to be able to do that. And I have some sample code here that basically you just run the document clustering, and then here I use latent semantic analysis and break it. You can change the number of components. So here I use 3, but you can use 4 or 5, and it'll basically cluster. It will basically cluster your documents. And here again, there's some about space. There's some about graphics. So sometimes some of the words are the same. So maybe you could try a different grouping number. So in this case, some's about space. Some is about like God, because I think there's religious. So these are the data set here is a set of news groups, and some are about atheism, some's about religion, some is about graphics, some's about space. And you can see here that it will naturally cluster into various groups. But as you can see, just changing the number of components in the latent semantic analysis will give you a different set of clusters. So sometimes you would want to play with the way that you reduce your data as well. And I'll upload the code for this. I think that it'd be easier if you just try and read a couple of the documentation on decomposition first, and only really use this if the clustering that you're using is giving you problems. So that's why I don't want to present it in full. Something else I wanted to show you that was pretty interesting is, again, with dimensionality reduction. One way to do it is you can actually find the principal components and then just represent it using those. So a great example is if you want to do image compression. So let's say you have an image and it has a lot of colors, like 600 or 700 different colors. One way you can use principal component analysis and find the principal colors that the image is made out of, and then represent it by that. Another way to do that is actually using k-means. So you can take the RGB values, so the color values, and cluster them to find the, let's say, 64 clusters. So instead of 600 clusters, you can actually use 64 clusters. That will reduce the amount of colors that you use, but still make the image look nice. And I had an example of this with an image from China. So this is the original image. This is with 615 colors. Here I used k-means clustering to literally cluster the colors. So instead of 615 different colors, I only used 64. And as you can see, it looks almost identical. This one's a little bit more sharper, but this one is greatly reduced in size. So that's a kind of cool application. And then if you want to do it without k-means and just doing it randomly, you can see here the colors actually look a lot. Personally, they look a lot worse. Whoops. They personally look a lot worse. So if they aren't as vivid as using k-means, so that's another way that you can use k-means to be able to do your analysis. So again, for your projects, what I recommend doing is first just simply try different number of k. So basically just use the simple k-means and just vary the number of clusters and see what the results are and try and visualize your data. And then if that's not working, you can try other algorithms. So that's mostly what I wanted to present today. And the other thing you can do is also read the documentation, because they have quite a few examples of ways that you can cluster and the different advantages and disadvantages for each of them. And you can also look into dimensionality reduction, which is, I believe, the previous topic in the documentation. So if you look up basically in the unsupervised learning documentation, it shows you various different techniques you can use. So of course we can't go over all of them, but going through at least the clustering and the decomposition will be pretty helpful. So I'll leave the rest of the time to help you guys with your projects.